so I'm going to talk about the PHENIX future, the physics with sPHENIX. And so I got this title, and I thought about these talks with the past and the present and the future. And of course, this brings up The Christmas Carol by Charles Dickens. So I, being an idiot, typed The Ghost of Christmas Future into Google Images to see if I could get an appropriate picture to put up here. And I got this. And I thought, wow, Barbara hates me. But this isn't the kind of talk you want. You don't want a grim talk about all the things that could go wrong in the future. Let's have a happier talk. And so if you look underneath this delightful, unoffensive holiday tree, look, if you open the presents, there's sPHENIX. All right, so RHIC, the past and the present, as we've heard, really, I'm going to talk about the study of the quark-gluon plasma. So really the goal is to produce and study dense QCD matter. And we've heard a lot already today about the things that PHENIX and the RHIC program in general has done in order to do this. And PHENIX has done a lot, of course. We've studied the flow of various particles, not just the V2, but also the V3 and the V4. We've studied the suppression of various high PT particles out to very high PT. We've measured thermal photons to get a handle on the temperature of the matter. We've really tried to address the properties in the best way possible. And one of the things that I think is a hallmark, really, of PHENIX is an emphasis on detailed measurements. So in PHENIX, we not only measured the J psi, we measured it as a function of rapidity in a whole bunch of collision systems. This is in d gold collisions to try to get a handle on the initial state effects, really so you can extract as much physics as possible from these sorts of things. And as we've heard a lot about in Dave's talk before, we didn't just measure the suppression of pi zeros. No, we measured the suppression of electrons from heavy flavor decay. And of course, with the VTX that's going in, or that's already in, we will get better measurements on exactly this sort of quantity. And we weren't even content with measuring the just electrons from heavy flavor decay, but rather we spent a lot of time trying to separate out bottom from charm electrons. This is in PP collisions, where we can actually do it. And so PHENIX is really, I think, a hallmark, just trying to get at things in the most detailed and precise way possible. And so where has this really taken us? And this is really us as a field, I think, here. So this is the V2 and the V3 as a function of the number of participants. And what we're actually doing now is we're zeroing in on eta over s. I mean, Bill talked a lot about this. But we're really able to put numbers to this. This is distinguishing between two models here using V3. One with a Glauber initial condition and an eta over s of 1 over 4 pi. And in the red one, the one that failed here, is a KLN initial conditions and a higher eta over s. So this isn't saying that we know exactly what eta over s is, but we have the tools in order to really distinguish between different competing models. And I think that we've learned a lot from this, and it's required a lot of good experimental data and having the theoretical models in order to interpret this well. So we're still working, I think, to get at this kinds of consensus and quantification with other properties of the matter. And so that's what I want to talk a little bit about right now. And in the last year, of course, now the LHC is also a player in our field. And they've taught us a lot, and they've changed a lot about how we think about these sorts of things. So of course, some of what the LHC has done is to just simply look at the same sorts of observables that we looked at with RHIC, only at higher energies, both higher energies in the observable and higher collision energy, of course. So this is the RCP, the suppression, but this time it's full jets, from 100 GeV to about 200 GeV as a function of centrality. And what you see here from the ATLAS experiment is that even out to 200 GeV jets, which is the highest that they so far go, the jets are suppressed at the level of about a half. There doesn't seem to be a large PT dependence here. These points are all at about the same spot. But so, this is just a plain old RHIC-style observable. We don't have it with jets, especially at 100 GeV, but this is just the same sort of thing that we've been looking at. Actually, of course, they've looked at very similar things also. This is the ELISE charged hadron RAA, and it actually is not only the same type of observable that we have at RHIC, they got pretty much the same answer as the PHENIX pi zero result, going out to about 20 GeV. The black points are from PHENIX, and the red points are from ELISE, and they really agree. So the hadrons are actually suppressed at about the same level as at RHIC. Of course, the LHC has brought us new things. They have different sorts of data, and so they've measured things that we really haven't been able to do so well at RHIC yet. So this are jet fragmentation functions, both transverse and longitudinal, from the ATLAS experiment. And there's two sets of points here. One is central and one is peripheral. It doesn't really matter which one is which because you can see there really is no strong modification of the fragmentation function. So these jets are suppressed, but once you find a jet, it looks pretty much like it does in peripheral collisions, even if it's in central collisions. The CMS experiment has actually taken this maybe a step further. They trigger on a jet, and then they look on the away side at hadrons. And what they see is a deficit of high PT hadrons inside the cone. But then if you look at low momentum stuff outside the jet cone where you expect it to be, so this R, delta R greater than 0.8, that's where they recover the energy. So the energy is lost, and it seems to just be very far away from the jet axis. It's just not there. It's not recoverable as part of the jet. So this is actually very interesting. And what it's done is we see things that now there's really strong energy loss both at RHIC and the LHC energies. That's not in dispute at all. And the lost energy is really transferred from the jet to the matter at large angles and at very low momentum. And so these results actually really challenge the sorts of radiative energy loss models that are based on the RHIC data. And so there's various new ideas out there. There's a whole bunch of them. You can probably see them on the archive. But there's a lot of strong constraints from needing to describe both the RHIC and the LHC data. What we look for in the future, hopefully, is RHIC results for these new LHC styles of observables. And it's really key that they be of comparable quality so that you can really put them on the same plot and calculate them with the same models. Of course, just a disclaimer, jets are not the only topic out there. They're just the one that I like to talk about, so most of this talk will be about that. One other topic that we're very interested in for sPHENIX is, of course, Quarkonia, which is a good probe of the screening length of the matter in various different states and such. So I'll say a little bit more about capabilities for that at the end. So how do we face the future? If it's really as grim as maybe it seems, calorimetry is a good idea, right? You want as much lead as possible between this and you. So including hadronic calorimetry for excellent jet capability, something that is commensurate with what they can do at the LHC. So you can really compare the jet measurements that you would make at RHIC to the ones at the LHC. And lots of acceptance. And high rate capability. So PHENIX obviously has high rate capability, as Dave just told us, and we all know. Lots of acceptance is not PHENIX's strong point, but both of these are really necessary to take full advantage of these rare probes that we're interested in now. Electron identification is also very important, both for Quarkonia and for heavy flavor. I mean, Dave, I think, did a very good job of explaining that we're very interested in heavy flavor both now and in the future. And to keep that, you need to have electron identification. And of course, this is a hallmark of RHIC in general, which is the system and energy versatility. We're not just stuck at 200 GeV. We can go lower to energies where you still have sufficient statistics for rare probes. And we have run various different kinds of species, including D-gold and such, to get good reference measurements to understand the initial state, which we also know is very important. So we've put together this sort of sPHENIX concept. It's not really please don't take the numbers on this too seriously. But the idea, especially at mid-rapidity, which I mostly want to talk about, is something that keeps the current VTX and FVTX, maybe adds a couple of additional tracking layers, pre-shower detector, EMCal, and HCal inside a solenoid magnet. So this would maintain the current high rate capability. And the advantage of that is you get to take a lot of data without having to bias yourself by triggering in heavy ion collisions, where you start to really bias yourself as to what sort of jet modifications and such you're looking for. Retain the current silicon detectors because they're new now, at least. Large uniform acceptance, which is, of course, would be great to have in PHENIX. And hadronic calorimetry mid-rapidity is really the first at RHIC. And this provides the jet resolution and the efficiency because, of course, a lot of the energy ends up in hadronic energy to extend to very high PT. I'm not going to talk about the forward detectors because Christine is going to deal with all of that in the next talk, but suffice it to say that the forward detectors really drive the design and for spin, asymmetric collisions, and future electron-ion collider. So this, I'm sure Christine will discuss. So how do we take PHENIX and evolve it into sPHENIX? So this is a side view of PHENIX as it exists, mostly right now. So if you're going to put something new in, you have to get rid of other things. So, of course, this is much easier in PowerPoint than it is in reality. But the idea is to get rid of the central magnet and the central arms, and at least one side of the muon detector, probably, and replace it with something that is compact. Because this isn't necessarily a general purpose sort of detector, and we also have size constraints. It doesn't have to be super huge. This exact size is still under consideration in design and such. This is just sort of a cartoon right here, but to put something like this at mid-rapidity. All right, but then of course what you're all thinking is really jets at RHIC, this is the LHC's strength. So is this even possible, or is this a real physics program that you could actually have at RHIC? And I think it is. First of all, there's a factor of 30 difference in beam energy, right? So there has to be different things going on at RHIC and the LHC. The early LHC results certainly seem strikingly RHIC-like for the RHIC observables, but how does RHIC compare for the new LHC observables? That's something which we don't know the answer to yet in the great detail. And I already made this point about comparable quality. And also, everything we know from the LHC is based on one short run that happened last November, right? So they're getting new data now, or they just did. But I'm sure, I would be surprised if there were no surprises, right? So what else are we going to learn from the LHC? I don't think we've learned everything we're going to learn. And so all of this together will determine the physics that goes into really a coherent theory of parton-matter interactions so that we can make the same type of plots for Q hat that we are for eta over S. And actually, the jet rates at RHIC are not insubstantial. So this is a plot from the PHENIX decadal plan. And so if you take projected RHIC luminosities in a 20-week gold-to-gold run, you could sample something like 50 billion events, of which 25 billion might be minimum bias events. And so if you start looking out here, you're looking at, say, maybe 1,000 jets above 60 GeV. So these are light jets here in the red. And if you look at direct photons, maybe about 1,000 photons above, say, 30 GeV, which is quite a lot. And if you compare that to the black curve, which is the pi zeros, you see how much further you get in PT just by going from pi zeros to the full jets. We're losing a lot of the cross-section right now because we don't have this full high-acceptance jet detector with the hadronic calorimetry. If you just look at pi zeros, you miss a lot. And so this plot here just shows the increase in acceptance for various channels compared to an sPHENIX type detector to PHENIX now. And you see for dijets, you get something almost a factor of 100 increase. And for Corconia, you get something that's well over a factor of 10 increase. So these sorts of increases really allow for qualitatively new measurements. Not only jets, but dijets, those are jet correlations, hopefully something in jet shapes, Corconia, heavy flavors. And so actually about heavy flavors, if you take this same plot I showed you and you now overlay the black line and the red line, which are both charm and beauty jets, as you expect them to be produced, something that you could go out to above 30 GeV. And so these are substantial heavy flavor jet rates, and I think that really having heavy flavor jets is also necessary for bringing together a coherent picture of what's going on with energy loss. So we've actually been doing a lot of work. There's a lot of people in PHENIX who are excited about exactly this idea. So one thing you do if you want to build a new detector is you do lots of simulations. And so can you actually measure these jets? I mean, it's all fine to just plot PQCD curves, but what can you actually do? So we took standard hydrogen events, and we identified the true jets. So we actually run a jet finder on the product of fragmentation calls within the event generation. So this lets you know what hydrogen thinks the jets are. And then you find the reconstructed jets within hydrogen using an iterative event-by-event background subtraction method. So this is largely based on what Atlas is actually using. Brian spent a lot of time helping us develop this. And we use the FastJet's anti-KT jet reconstruction algorithm, which is really state-of-the-art for heavy ion collisions now because of the way it deals with the background. And so then we find the fake jets. So you can match up the reconstructed jets with the true jets. And if they match, that's a real jet. And if they don't match, that's a fake jet. And so the fakes are just from things in the underlying event fluctuation that you have. And so this is a preliminary plot from R equals 0.2 jets that Ali made. And what you see, the fakes are shown here in black. They die off. They look sort of exponential. And the blue ones are the matched jets. And you see that they cross over the fakes at something like 20 GeV. So this had jet energy resolution and such from the hijing in it. So there's good evidence that we can actually see jets above 20 GeV for these smaller jets in central 0 to 20% worst case scenario collisions. So of course, as you go to wider jets, the background becomes worse, and we're investigating that, of course. But if you also go to correlations and do things like that, then you can suppress the background, as we already know. So, I mean, this is a preliminary plot that these jets are not, this isn't just made up. Of course, Quarkonia is also a subject of great interest, and so this is a upsilon plot from both Phoenix and Star in D-gold collisions. And so you can see the Phoenix points out here, and they show what looks like maybe some interesting physics, but the error bars are, of course, large. But if you increase the acceptance by a factor of 10 more and go to these higher luminosities, then you have the ability to have much more precise measurements, where you can actually start to do more physics, especially with the upsilons. And so we've actually done some simulations on these. These are, again, from the decadal plan. If you had muons, which is one thing we're talking about, then you could really start to separate out the upsilon 1s, 2s, and 3s states. If you go to electrons, you have a little more problems from the radiative tail. However, there's still the ability to separate the 2s and the 3s from the 1s states. So there's and of course, you could also measure J size in the various Quarkonia states. So there's a lot that can be done from Quarkonia in the same manner. All right, so beyond mid-rapidity heavy ion collisions, I've talked a lot about that. The spin, EIC, and cold nuclear matter programs are really what drive the forward design here, beyond eta of 1. The entire sPHENIX detector does not have to go in on the same day. It doesn't have to be something that you just order from Amazon and it comes in a box and you plug it in. But it is important to have a coherent strategy or a coherent concept from the beginning so that you don't have a bunch of mutually exclusive pieces. And that's what we're trying to do right now. So transforming sPHENIX from a cartoon to an actual design is underway. And we're actually doing a lot to make this real. So we have weekly meetings, which is probably not that exciting to hear about, but we do get a lot of people to come to them. There's a smaller subtopical meetings, for example, on the forward and spin stuff and jets. And next week, over 20 people are going out to Colorado, not to ski, but to spend their time in a room devoted to simulations, designs, cost considerations. And this is actually the fourth in a dedicated sPHENIX workfest. So these are week-long things where people really give up their other commitments for a week and devote their time to this. And this is really a good way for us to make a lot of progress. So sPHENIX. Really, I think one of our main goals is to really advance the understanding of the quark-gluon plasma. And what makes this unique is the HCAL, the high rate, and the large acceptance. This is really something that doesn't exist so far at RHIC. So it allows qualitatively new measurements, quality jet measurements, dye-jet measurements, Quarkonia measurements, and the ability to really do a lot of heavy-flavored jets. And there are, of course, new opportunities for RHIC and spin, which Christine will talk about. And having quality RHIC and the LHC measurements is crucial to really developing a quantitative understanding of the quark-gluon plasma. And so this type of detector really allows you to do a broad range of QCD studies within a single experiment.